Hello, Leonard Martens again from Ghent University and VIB. We're now at the 5th installment of our lectures on mass spectrometry basics. Just a brief recap as usual. We talked about amino acids and their properties, how they influence our analytical setup for the mass spectrometers. We talked about the mass spectrometers themselves in the second lecture, about their components and overall architecture, and the ion sources. That was the second part of this second lecture. Third lecture was talking about the different analyzers that we have. And the fourth lecture, the previous one, was about detectors. So how do these detectors work and what are the caveats with these detectors, which are quite important for quantification. Now we come to two special beasts, and that will sum up our entire talk about the instrumentation, is the Fourier transform, ion cyclotron resonance, and Orbitrap instruments, because as I said before in the previous lectures, they actually combine analyzer and detector in a very interesting way. So let's go and look at these very fancy instruments. We'll start with the oldest one of the two, the Fourier transform ion cyclotron resonance instrument. It's a very long name, but the name is extremely apt. Just like MALDI, matrix-assisted laser desorption ionization, is an apt name, this one is apt too, and we'll work our way through it. The first thing we'll focus on is the fact that it's an ion cyclotron. So an ion cyclotron is a very fancy device that uses magnets, very, very powerful magnets, that of course influence electrically charged ions, by forcing them to move in a circular path. And it's an endless circular path, so they keep cycling through the electronics. It's a cyclotron. The electron or the electronic components make the ion cycle. So an ion cyclotron. Very big ones are built in CERN, or by CERN in Switzerland. As you may know, in Geneva, the Large Hadron Collider is essentially a really big cyclotron. These, of course, are a little bit smaller, but they're still very sophisticated. The way you make magnets that are powerful enough to keep these ions in a cyclical orbit, if you like, is to use superconducting magnets. And superconducting magnets need very, very low temperatures. In fact, they have to be below 4 degrees Kelvin, which is very close to absolute zero at 0 Kelvin. And it's roughly about minus 269, 270 degrees centigrade is where these magnets operate. And the only way you can get them that cold is by cooling them with liquid helium. Now, helium is a finite resource, it's quite expensive, and also this is very tricky, because in order to make liquid helium, which is very apt to escape if it evaporates, you need very sophisticated machinery, you need a lot of power, and it has an electrical power, and then finally, once you have the magnet generates such a strong magnetic field that nothing made out of any magnetic material like iron or steel is safe when it comes close to these magnets. It's the same like with NMR devices. So don't wear any steel rings or steel jewelry, because it will just tear off your body, and it will probably take some body parts with it. Now, usually they shield these things these days, but that costs even more power. So you've got a huge, heavy, sophisticated, complex, easy to break, expensive to maintain device. Why would you build something like that? Well, for a very good reason. Our very strong magnetic field and our set ion orbit is a really great way to analyze masses, inertial masses again. You know what happens when you have an ion and it moves around in space? If I were to put a metal plate here and I move the ion next to the metal plate, I'm going to induce a current in this metal plate. And so by putting two electrodes on opposite sides of this cyclotron, which I show as a box, in principle it's not a box, it's more like a ring, of course, these ions will now induce currents in these plates, and the currents will spike at the rotational frequency of the ion. So every time the ion passes, it gives off a little spike. So if the ion goes really fast, there will be lots of spikes. If the ion goes slow, there will be fewer, more widely spaced spikes. So in a way, the speed with which the ion moves, which if you remember is related to the kinetic energy, which is related to the size, or the mass of the molecule, can be read out from the spike distance of the electrodes. So the electrodes measure the time it takes as an individual spike each time for an ion to complete an orbit. Now, if we had a pure ion, a pure M over Z in there, this would be really easy. And we would just look at the spectrum and we'd see peak, peak. We would measure the distance. We'd say it takes the ion so long to get round, and that actually gives us the M over Z through some mathematics. However, this is not the case. Usually, there will be many more ions than just one in this cyclotron, and they will have all different masses, the result of which will be a superposition of, say, the slow ion that goes beep, 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 and the very fast one that goes beep, 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 beep. The total net signal that we will get from our electrodes is the superposition of all of these signals, the slow ones and the fast ones, and it will be a huge jumble. So the ion cyclotron resonates or creates resonance currents in the plates. That's the ion cyclotron resonance. But the resonance signal is a mess. So how do we tease all the individual molecules apart? This is where our French mathematician friend Fourier comes in. And Fourier made this beautiful theorem which says that you can take any curve, any function, and represent it by an infinite expansion of sine waves. Now, that is exactly what we're going to do. We're going to use the mathematics invented by Fourier to decompose this jumble of the resonance signal into the constituent frequencies. And when you do that, you actually get the single frequencies of all the ions in the sample. Now, it's not entirely true what I say. It's not every single ion. The problem is you need an infinite expansion of sine waves. And of course, your computers who have to calculate all of this do not have time to calculate an infinite series. So we use tricks and we try to calculate something reasonable. But the problem is that in doing so, what we are actually going to end up with is a good approximation of the original composition. So we may not get everything, but we get a very good approximation. And the masses that we get from the Fourier transform frequencies, and so these frequencies, of course, as I said before, like for the pure ion, we can calculate to the masses, they're very, very accurate. Why are they so accurate? Well, remember the time of flight? And in the time of flight, we had a certain length, and then we timed how long it took to traverse the length, and that gave us the speed. Here we measure something very similar. We measure frequency, which is how often do you pass by the plate on this rotation. And we know the rotation because we have a fairly good idea of what that cyclotron looks like. But we don't measure it once, like in a time of flight. We actually measure it once, twice, 3 times, 4 times, 5 times. You measure it for as many times as you like while you keep the ion in the cyclotron. Now, for practical purposes, you tend to occasionally throw out, it's like an ion trap, this cyclotron. So occasionally you have to throw out the ions and let new ions come in because they tend to come off a liquid chromatography gradient, as we've seen in the second lecture when we talked about the electrospray source. And so you have to occasionally recycle them and throw them out and get new ions in. But you can keep this going for a while. And the longer you keep the ions in the cyclotron for, the more accurate your measurement will be. So you have to balance between how fast do you want to analyze something and then move on to the next bit that comes off your gradient versus how accurate do you want it to be. But the accuracy is enormous. Remember when I showed you in the lecture on the mass analyzers, we talked about the resolution, and I showed you these graphs that had these Gaussian shapes. Compared to what I showed you there, a Fourier ion cyclotron would give you a straight line. It would be so narrow, the resolution would be so incredibly high that the only way you could represent that at the isotope level would be to draw lines, straight lines. So it's extremely good. The downside of this is it's a huge beast, it's very hard to maintain, and you even need to reinforce the floors you want to install the thing on. It's very difficult to operate, it can break down very easily. So it gives you the best performance possible at a high cost, both in maintenance and in actual cost. As a result, they're not that popular. People use them, but they're not that popular. The expense, the hassle, is the reason why they're not used so much. Now, we can introduce the Orbitrap. The Orbitrap was invented by Makarov, and it's a very recent invention. And it's a beautiful design that is very, very simple, yet it achieves very much the same kind of resolution as a simple Fourier transform ion cyclotron resonance instrument. It's not as good as the top-of-the-line Fourier transforms, but it can approximate them very closely. Let's have a look at how it works. This is an ion trap device. As you can see from the name, it's an Orbitrap. But rather than trap the ions back and forth, it actually has this very strange design with an outer hull that is droplet shaped, and then an inner hull that is shaped like a double cone. And what is going to happen is we have electrical fields. As you can see here, they're electrodes. We have electrical fields on this, and the fields allow the ions to move around the central spindle, and they go back and forth. Now in this looks like a Fourier transform ion cyclotron resonance. Remember, where the ion cyclotron is concerned, the ions cycle in the cyclotron, and we have these two plates, and they measure how often they pass. You could imagine doing that here, because you also have a central spindle that the ions circle around. Unfortunately, the physics are such that you cannot easily get mass over charge from this rotation. But apart from the rotation around the central axis, there is also precession. So if this is my central axis, this is the rotation around the axis, the molecule is also going to move back and forth. And it is this back and forth movement along the axis, the precession movement, that contains the mass over charge. It's very tricky to read out that movement, because you have electrodes, you have ions moving around in many directions, and the real trick of the Orbitrap is not getting the ions to make that movement. The real trick is to read out the current that is induced by moving along the spindle electrode. But as soon as you can do that, you get a frequency again, and the frequency is the back and forth frequency along the spindle, and that is a superposition of all the ions that are jostling for space in that trap, and again you need a Fourier transform to deconvolute that into the individual frequencies. So it's very similar to the ion cyclotron resonance instrument, but it sacrifices the whole complexity of having a cyclotron in which the ions make simple movements for a much more complex movement in a much simpler device. The size of such an Orbitrap is around about this big. It's about 10 centimeters, and these things are practically indestructible. Once they're made and they're operational, they will continue to work practically forever. So this is a much simpler device that works in a very, very good way to give you a large amount of resolution at minimal maintenance cost, a little bit of a higher purchasing cost, but at least they're very, very accurate and very precise. The reason, of course, why they can do this is exactly the same. We actually average out many of these back and forths, and that actually allows us to measure a very accurate mass. Similar to a time of flight that we do many times, and like the Fourier transform, the more often we do this, the better the result will be. So with that, we come to the end of the special cases, the Fourier transform ion cyclotron resonance instrument and the Orbitrap, and our next lecture will be tandem mass spectrometry and how that works in the instrument. See you then. Bye-bye.